A video on adding a shunt, a standalone shunt, to an existing solar system. The solar system in question in this case is going to be a 48 volt system that has what we call an all-in-one inverter charge controller type thing. So we're just going to kind of build the basic system, and then I'll show you where the shunt needs to go and why it needs to go there and such. So let's start with, we've got a box here that is, it converts 48 volt, what we call 48 volt to 50 volt DC from a battery into AC for use within the house or the RV or something of that nature. Now, for that to work, it obviously needs to be connected to one or more batteries. We're going to show the battery as being a rack of these rack mount batteries. Now, this doesn't have to be 48 volt. This could be a 24 or 12, but oftentimes when we're getting to this kind of system, it's going to be what we call the 48 volt battery systems. Okay, so we've got our battery system here. It's going to be connected to the inverter, and we're going to have red, which is going to be your positive, and black, which is going to be your negative. So let's say you've just got one battery and you're connecting it up there. Battery's got a charge on it. We're just going to assume the battery's got a charge, and these are the only two devices. You turn this on and it's going to generate AC outlet or AC power. But let's say that we now have a power strip, which can be done. It's also kind of good, might be good if that was an actual circuit breaker panel, but just for argument's sake and simplicity, let's say that we've got a power strip. Now that power strip is going to be connected to the all-in-one up here. You're typically going to have, and in this case, I'm more worried about the DC side for the shunt. So for this, I'm just going to go ahead, let's call this one a little bit thicker, just to show that it's not, this is not DC. I'm going to use this kind of funky thing going up. So this is going to be the AC out coming from this to the power strip, and it's going to have all three wires in it. It's going to have the ground, the neutral, and the negative on that, just to show this is where the AC is. So this will work. So if we've got power in the battery, it's connected to this, it will turn this on. This will consume a certain amount of power. It will generate the 120 volt AC, which will go to our power strip, which we plug our appliances in. All good and well. In setting it up, this device, you tell it that it's a 48 volt 100 amp hour battery, and it will try to keep up with the state of charge. Assuming this is full to start with, it will try to keep up with the state of charge of the battery, as well as the battery itself will try to keep up with its own state of charge. Some of them will have a little display on them. Some of them have an app. Some of them are able to actually use kind of a version of network communication with the inverter up here, and the inverter, instead of trying to keep up with state of charge and all that itself, it will just take the information directly from the battery. All good and well. Now, at some point, we're using the power, even if we don't plug anything in. This is using power just being turned on, and the computer board in here is using a little bit. So eventually, you're going to need more power. So we get that more power from the solar panels. So your solar panels, and this is going to be whether it is a single panel or whether it is several panels that are wired together to act like one panel. So you can actually wire these together in a way that they act like one panel. They're going to be connected to this, and anytime there's enough light, they will generate power, which will go into this inverter charger, and it will take, it'll take this and turn it into AC. And if there's more power coming in than it needs to use to generate the AC that you need, then the excess it will put into the battery. If there's not enough coming in from the solar, or it's nighttime, then it will pull from the battery to generate that. So it's got two different sources of power coming in to supply power to your AC loads and to recharge the battery. Now then, if you have more than one battery, in this case there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 in this one. Then how do you wire the batteries to the inverter? In this particular case, you see it going, if this is the positive, you can kind of see they're going from battery to battery to battery to battery. So these are all positives, going positive, 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 all the way down, negatives all the way down. And they would take the positive here, the negative all the way down at the bottom, whether it's 2 batteries or 6 batteries or 10 batteries. And in that way, all the batteries are getting pulled from at the same time, and they stay balanced. If you just put the positive here and the negative here up there, then over time, this battery is going to be supplying and receiving more of the energy coming in and out. It's getting worked a lot harder than the one way down here. So to balance that, you go diagonally. Or, another way to do that, you can take what are called bus bars and insert them so that each battery, positive will go to the positive, negative will go to the negative. So if I try to draw that, if it will let me, we would basically be going from positive to positive, positive from this one up there, positive from this one up there, yada yada yada. Negative would do the same thing. We go from negative, 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 okay? And just each battery is done that way, and one of the key things you need to do on this is all the positives need to be the same length, all the negatives need to be the same length. So even though if you mounted this right at the top, and this battery is very close, don't put a very short cable from this battery to the bus bar and then a long one to that one. Start at the bottom, and whatever that longest one is, make them all the same length and the same wire, same diameter wire. One of the things this does is keeps them more in balanced. And also, if you happen to have an inverter charger or a system that is really, really big, and let's say that it could put out 10,000 watts. 10,000 watts, the amount of power that it would need to be pulling from the batteries is well over 100 amps. A lot of these batteries can only put out 100 amps each. And if you wire them in series, that wire may only be able to hold 100 amps without overheating and melting or shutting down the battery. By doing it this way, a bus bar, whether it's this kind or whether it's mounted into the frame, then let's say in this case we've got 3 that are wired up and we're needing 100 amps coming up. Well, they're dividing the load equally, so each one of them is doing about 33 amps, which is well within the limits of the battery, and hopefully, if we've got the right wire of the battery, of the wire going up, and then this bus bar is able to hold a lot more than that. So this is just a way of balancing the load not only on the batteries but also on the cabling, on the wiring, and making sure no single component is over its rating. Now, if you've got cables here that can handle 100 amps and you're needing up to 300 amps here, then of course the cable going from the bus bar up here needs to be able to handle that 300 amps plus a safety margin. But so let's say we've got this as the wiring. Now, where does the shunt come in? Because at this point, if you might tell the charge controller that you've got, in this case, a 300 amp hour battery bank, and it may be trying to keep that up, keep up with that as far as how much power is coming in, how much going out, and what the state of charge of the entire battery bank is. Each battery is keeping up with its own state of charge. And even if everything's perfectly balanced, the BMSs, the electronics in these batteries, are just known to not be that accurate. And if you're not charging this up to 100% like every 2 or 3 days, if you're going up to, from, let's say, 30% up to 80%, back to 30%, back to 80%, they're going to start disagreeing with each other. This one's going to think that it may be at 80%. This one's going to think it's at 70%. This one may, for some strange reason, think it's at 30%. And eventually, no matter how much energy is in that battery, if the electronics in it, if the BMS in it thinks that it's down to 5%, and that's what's been set as a safety margin, it's going to turn off. And when it turns off, then even if it's got essentially the same amount of energy left as the other two, then you're now only working on these two until you get enough, until you recharge the whole system. Every time you go to 100%, they all kind of reset to 100%, get back in sync with each other. The ones that do communication, they will actually have a network cable going from there to there to there. They'll talk to each other, kind of keep things in line a little bit, and then if you're really lucky and that communication can talk to the inverter up here, then that kind of works a little bit better. Communication gets more important as you have a bigger system and more batteries and more components. So, if we want to keep up with the state of charge of this stack of batteries, whether it's 2 or whether it's 10, and each one of these are not talking to each other, or even if they are, they're known to not necessarily be the most accurate, what can we do? Well, we can add a shunt. Now, before I make it small, one of the important things about a shunt, regardless of the brand, is it goes in line, unless it says otherwise, and I haven't seen one that says otherwise. It goes in line on the main negative cable leading to the battery. Because what we're measuring, the only thing that we want to be measuring here, is the battery or stack of batteries, bank of batteries. So we want to keep up with every electron that goes in and out of this stack of batteries. So it goes on the negative, and it goes a certain way. There will be one post that goes to the batteries, and the other post goes to the rest of the system. This other post becomes the negative for the entire bank. So if we don't have it in there, we can just put any negative on any one of these posts. So all the batteries are connected. This can be connected. Any other load, charger, whatever could be connected there. But we're not really keeping up with the total amount of energy going in and out of the battery, how big the battery is, and keeping up with that state of charge. Think of this as the bouncer or the security at the front door of a bar, or the flight attendant at the door when you're boarding and disembarking from a plane, or the accountant for your bank account. Every electron going in or out of the battery has to go through this for it to keep an accurate count, an accurate counting of the state of charge of this battery. And it does take a little bit of power itself. But look, what we're going to do is we're going to put this, see if I can make it small enough, on the negative. Okay, so it goes on the negative above, between these bus bars and your charge controller or any other devices. So with this connected, then you've got 3 100 amp hour batteries. You would tell it via the app that it is a 300 amp hour battery bank. If you added a fourth one, you'd go in there and tell it it's now at 400. Now, it's not going to have any idea how much charge is in, how much energy is in the battery bank until it's charged to 100%. So you go into the app. In this case, I usually use a Victron with a smart app, and I go in there and say it's a 300 amp hour battery, and when it is fully charged, it might be at 54.8 volts. That is fully charged. So when you start charging it, eventually the voltage that it can sense is 54.8 or 55 point whatever the batteries say they need to be at, and it will hold it there for a certain amount of time, meaning no more energy is going in, and it will automatically set to 100. And from that point, any time that there's more power going out than in, it will start subtracting from that 100% state of charge. Doesn't matter what brand, doesn't matter if every one of these are different brands, doesn't matter if you've got a 50 amp hour, a 100 amp hour, and a 600 amp hour. They're all 48 volt batteries. You can add that up at how many amp hours it is, and it keeps an accounting of how much is going out, how much is coming in, and this becomes your point of truth for the state of charge of the entire battery bank. And it tends to be as or more accurate than all the rest of the stuff. And you can just pull it up on an app in your phone and see where you're at. Some of them may have a display, something of that nature. So this gets you up and running, and you're good to go. Well, what if you start adding more things to the system? Okay. Let's say you've got 6 panels, and however they're wired, series, parallel, or a combination, from the panel, that is, there's only 2 wires leaving this array of solar panels going to the charge controller. Let's say that you end up with a second array. It's in a different place, it's newer panels, whatever. For some reason, you end up with a second array of panels that you need to add to the system. However, you're already maxed out on what this wire can handle, or for whatever reason, and there's a charge controller in this one that's already used. So how would you do that? Let's add just a standalone charge controller to the system. So here, exact same way you did the other one. You have your negative goes to it. You have your positive goes to it. You have your negative goes to it. Now, so this is the solar direct current coming into the charge controller. Now, where do you wire this one in? Do you wire this directly to the bus bars? If you wire this directly to the bus bars, you're going to be bypassing the shunt. It's not going to have any idea that there's more power coming in. So this would be coming in the back door. It doesn't know anything about it. It'll see that the voltage may be rising, and when it gets to the right voltage long enough, it'll say 100%, but it can't account for it. It's coming through the back door. So what you do in this case is the positive from here can go to the positive on this bus bar. That's fine. However, the negative needs to go in to the shunt, so that it's going through the shunt, and then from the shunt to the negative bus bar, then to the batteries. That makes sense? So whether it's the energy coming in from these solar panels through this inverter going into the battery, whether it's the power from this array coming through this charge controller, it's got to go through the shunt, and whether it's the energy in the batteries coming out of the batteries to go up to the inverter to be used, it goes to the shunt. On the negative side, Everything, every negative goes in and out of the shunt. Nothing bypasses. Okay. Well, we're not done. You can have multiple charge controllers, okay? We could have this Victron here. You can add 2, 3, 4. You can have as many as you want. They can be different brands. If you're not worried about them all communicating through some app, and adding up and everything, electrically, they don't even have to be the same brand, but you can have several of these. This is charging from solar. This is charging from solar. Let's say that you've got just a dedicated battery charger. How do you wire that up? Now, all this does is takes AC and connect it to charge the batteries. Once again, the positive can go directly to this bus bar, not a problem. But again, the negative needs to go through the shunt. Otherwise, the shunt has no idea that there's energy coming from this device into the batteries. The shunt doesn't know if it's this inverter charger, if it's this charge controller, or if it's a dedicated DC charger. Every electron in and out has to go through this. If you're solar and you're off grid, how do you power this charger that takes AC and puts it into DC? Well, you do that from a generator. So this connection, no big deal. It's going to be your regular AC plug. It's got the 3 wires, your 110 plug, or if it's a really big one, it might be 240. But this just comes off the generator, goes into that, and it provides, in this case, 20 amps at the battery voltage. Positive goes in here, negative goes in there. If it is an inverter generator, meaning it makes clean enough power, you can go from this generator, oftentimes, into this and plug it in where it thinks that the grid is. If it has an option for grid power, you can plug it in there, and so long as the amount of power that this is supplying is the right voltage and it's clean enough, it will accept it here, and just like all the solar and everything else, it will pass that AC directly through to your loads. Any excess will go to the batteries or balance between the batteries and the generator. So you can do it that way. You can have multiple of these chargers. There has been an occasion where I've had 3 that look like this plugged in at the same time. But again, on the DC side, everything has to go through this. Now, let's say we're in this situation. So we've got a pretty heavy negative wire coming out of this. We've got a negative wire coming from this charge controller. We've got a negative wire coming from this charger, all going in here. You may be able, it's not best practice, but you can stack probably 2 lugs on this. However, especially if you're thinking about doing 3 or more, even if you've got 2 now, if you're thinking about a second, a third, a fourth one coming in, my suggestion would be get another negative bus bar. You only need a negative. Put it right here, so you've got a single cable going from the shunt to that bus bar, and then you can add all the rest of them to that bus bar. So you could end up with a negative bus bar here, and then a negative bus bar here. Multiple batteries go into this negative bus bar, single cable going up here, negative bus bar for all the rest of them. Just make sure that this cable here from the shunt to the inverter generator is heavy enough for the highest possible amount of DC load going through there. and also from the shunt to this negative bus bar are going to be your biggest cables. The rest of these just need to be appropriate. You know, if this can do 100 amps, you need that wire to be able to hold 100 amps, 100 amps, 100 amps. If this one pushes 20 amps, you need the appropriate wire that can, you know, do 20 amps with a safety margin. If this one's 20 amps, you know, each wire needs to be done appropriately. Now there are some things that there are some, especially Victron devices, that merge the shunt, the power in, what they call a distributor, and the power out, and the battery side, all more or less in one clean system with fusing and all kinds of stuff. But this is kind of a basic way of how you would add that shunt in line to keep up with the state of charge of a stack of batteries, accounting for all the energy coming in and out of the batteries. And that, again, that only works if you isolate the batteries and treat the shunt, maybe through a bus bar, as the negative of the battery bank. If you go around it, it's going to get out of whack. It's going to lose track of that. Hope this makes a little bit of sense. If it doesn't, feel free, get a hold of me and we can go over this a little bit again.